Hello students, welcome to Math 4411, Abstract Algebra 1. Before starting Abstract Algebra, however, let's have some discussion on preliminaries. More specifically, I'd like to talk about these three topics: some set theory, some function theory, and finally, equivalence relations. I'll probably end up creating 3 or 4 lesson videos here, and all those are going to be optional. If you feel comfortable, you can skip them all. After all these are preliminaries already covered in prerequisite courses. But no matter how advanced you are, I do recommend going through the one in equivalence relations as a review. Now, if you don't feel comfortable, then you can review them all. That's okay either way. In any case, let's begin. Let's begin with the easiest topic, elementary set theory, elementary naive set theory. All right, here we go. The first topic, sets and elements. What do you mean by sets, elements, being a member or not? Not both, not neither, those kind of things. Do you remember roster notation versus set builder notation? Well, I hope the answer is yes. If you feel uncomfortable with any of those, then you're not sitting in the right classroom. Next topic, subsets and supersets. If every element of a set is a member of the second set, then we say the first set is a subset of the second set, or equivalently, the second set is a superset of the first set. We use this kind of notation, A subset of B, or like this, A subset of B. These are equivalent. So this expression here, which I just highlighted in blue, versus this expression, which I just highlighted in green, they're the same. They mean the same thing. It's not like the relation between less than or equal versus strictly less in real number arithmetic. These two are different in real number arithmetic. But for set operations, these two mean the same thing. Subset can be visualized like this. If two sets share the same elements, then they are equal, like this. And that means A subset of B and B subset of A. The next topic, the power set. The set of all subsets of a certain set A is called the power set of A, and we use this notation, P of A. In other words, a certain set is a member of a power set. That's the same as S is a subset. So blue and green mean the same thing. Here's an example of a power set. It turns out if original set has n elements, power set has 2 to the n elements. The reason? Each element has two options: to be included or not to be included, to be or not to be, to be or not to be. So multiply all those, then you get 2 to the nth power. So no to everything, then we get empty set. Yes to everything, then we have the first set, original set. And then in the middle, we have all those non-trivial proper subsets. Speaking of proper subsets, we use these kind of notations to denote proper subsets. Subset, but not equal to each other. Proper subset versus proper superset. Now these two mean the same thing. If you want proper, then you have to use these crossing or that crossing. I'll try not to use these kind of notations, however. Too confusing. I spent too much time on second subsection here. Okay. Some set algebra. First complement, intersection, and union or difference, A but not B, those kind of things. How about some set operation rules? Well, we have all those algebraic rules: intersection version and union version, commutative, associative, distributive, De Morgan's law, absorption law, those kind of things. Do you remember them all? I hope the answer is yes. Okay, now let's go a little bit deeper. Let's consider set builder notation in a little bit more detail. Here is the correct notation for the set builder notation. It always begins with a pre-existing set and defines its subset. What did it do previously here? Previously we did this. See the difference? This one is not entirely correct. This one is. But we're talking about positive null totals, so it's got to be integers. So this is so obvious that we just abbreviate it out and then write like this. That's okay. So if this thing exists, but it's so obvious that we skip that, then that is okay. As long as the starting set exists, it's okay. But in some case, we can't do this because this thing does not exist or too hazy. In that case, we can fall into trouble. What kind of trouble am I talking about? Here's a very, very famous example by Bertrand Russell called Russell's paradox. The set of all sets that does not take itself as an element cannot exist. Look at this, R for Russell. The question here is this R belong to itself or not? If yes, then it follows the condition of R, and therefore R does not belong to itself. But then again, if R is not a member of itself, then, hey, it follows this condition. Therefore, R is a member of R. What's happening here? If R is a member of R, then R is not a member of R, and vice versa. There goes a contradiction. It's exactly like I am lying. You see, it's logically equivalent to, quote, I am lying, unquote. If I'm lying, then I'm telling the truth. And if I'm telling the truth, then I'm lying. Exactly the same thing is going on here. There's no way out. In other words, if you don't have this specified, this entire set builder notation can break down. Is there any way to improve it? Let's try this. What if I begin with the set of all sets and then get that part taken care of? Will it work? It turns out it's not going to work. And consequently, the set of all sets cannot exist. How? Well, let's go with the same kind of argument here. R belongs to R, then it satisfies this condition. So R is not a member of R. That's the same as before. Now, the converse is a bit trickier. R is not a member of itself, then okay, it satisfies this condition, but also it satisfies this condition as well because M is a set of all sets. Therefore, R is a member of R, and thus, if R belongs to R, then R does not belong to R, and vice versa, so we have a contradiction. Now, what if M is a little bit smaller? M is not the set of all sets, but it's a large set, but it doesn't cover everything. In that case, the second implication, that turns out to be okay. If R is not member of R, then okay, R satisfies this condition here, yes, but it may fail here because it may not be in this M. Remember, I just reduced this. That is, the set of all sets cannot exist, so I go down a little bit. In that case, R may go out of this M. So this part may not follow, and consequently, this part may not follow either, so no contradiction. But then again, if M is set of all sets, then there's no way out here. So this has to follow, and consequently, contradiction follows as well. Conclusion: set of all sets cannot exist. That conclusion aside, we still have a problem. We got the correct expression of the set builder notation, but it has some significant restriction. I have to start with a certain pre-existing set, and I can define only its subset. I cannot go larger. That's a problem. I want to build all those mathematical tools, but I can't unless there's something already. How do I mend this? Well, the roster notation will come to help. Begin like this. We begin with the empty set. Yeah, okay, empty set exists. Sets must exist, so we begin with empty set. And then create set of one element like this with the empty set. And then pair these two, and then we have the set of two elements. And then pair these three, not pair anymore, list these three and a set of three elements, and so on and so forth. In naive set theory, this is how you define whole numbers. 0 for empty set, set of no element, 1 for a singleton, 2 for the set with 0, 1, and 3 for set of 0, 1, 2, and so on. You see, up to these all defined, so put those together and you get the next set, and the next and next. Up to n minus 1 you know, and then list them all, you get n, and then and so on and so forth. Generalize a little bit further, you get this kind of expression which we call a successor. So n, which is 0 to n minus 1, and then take the union so that you get 0 to n. Unions always exist, by the way. That's one of the axioms of set theory as well. And consequently, you ended up with plus 1. If you repeat that, you're going to get arbitrary addition of positive numbers. You see, repeated k times, you're going to get n plus k. Now, if you invert it, you get subtraction. If you repeat the addition, then you get multiplication. If you invert that, you get division. Now, if you consider repeated multiplication of same thing so that you get square, cube, fourth power, fifth power, and so on and so forth, and then you take radicals, and then you invert those and you get radicals, you see, square root, cubing root, fourth root, and so on and so forth. Well, from this successor operation, we ended up building pretty much everything, all kind of algebraic manipulation, all kind of algebraic computations, addition, subtraction, multiplication, division, and radical, all come from successor operation. So from whole number, and then inverted, we get integer, and then repeated, we get multiplication, inverted, we get rational numbers, and then we can consider radicals to include some irrational numbers and so on. Real numbers are a little bit trickier, but we can do those too. That's something we're going to do way back in 2005. But in any case, here's a conclusion. We have all those sets of numbers, NWZ, QRC, and we use the double struct font. Okay, so much for set theory, or elementary naive set theory. We're going to meet again, and then we're going to discuss functions in a separate video. Stay tuned.